So in this video, we're going to talk about Euler's Totient Theorem. And again, this is a really important theorem in number theory. And if you haven't watched my video on Euler's totient function, then I recommend you to go to that video and watch it first because this theorem uses this function. So if you do not know what this function is, then please go to my video and watch it and come back to this video to understand what this theorem is. So Euler's totient theorem states that if n is an integer larger than 1 and another integer a and n are coprime, and again coprime here, it means that it's the same thing as relatively prime. So yeah, I just use another word here because it's coprime and relatively prime, they're the same thing, and they both mean that the two numbers have a GCD of 1. Yeah, this was discussed in the Euler's totient function video as well. So if n is an integer greater than 1 and a n are coprime, then we get that a to the power of totient n is congruent to 1 mod n. Yeah. So that is the Euler's totient theorem. And again, if you have watched the modular arithmetic videos and the FLT video, then you will know why this theorem is actually really useful. And it's because of power towering. And I don't know if that is the correct term for calling that method, but yeah. So if you do not know what that method really is, then I recommend you to go to the Fermat-Little theorem video or the modular arithmetic videos to look at what the method is, so that you can kind of attempt the problems here on your own as well. And so yeah, if you're watching this video, then I assume that you already watched the totient function video. But again, I'll just write the formula here again so that we can just look at it. So totient of n is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2 times all the way up to the dots. Yeah, 1 minus 1 over pk. Yeah, so that's the Euler's totient function formula. Where p1, p2, all the way up to pk are the distinct prime divisors of n. Yeah. So yeah, before you watch this video, make sure you watch this totient function video. So let's see why this formula works. How this works. So let's say we can just test out something. So totient of 12 again. Let's find the totient of 12 first as an example. So 12 is equal to the distinct prime divisors of 12 are 2, and 3. So this will be equal to 12 times 1 minus half and 1 minus 1/3, which is equal to 4. And let's take a number that is coprime with 12, which is let's say 5. So 5 and 12 are coprime. And let's see if this formula works then. So 5 to the power of totient of 12. Oh my god, my handwriting. Wait a second. Okay. 5 and 12 are coprime, and so that means that by the Euler's totient theorem, 5 to the power of totient of 12 will be congruent to 1 mod 12, right? Then 5 to the power of 4 is congruent to 1 mod 12, because we just found that the totient of 12 is equal to 4. And we can actually verify this. We can check that this is right, because 5 to the 4 is equal to 625. And that has a remainder of 1 when divided by 12, so it's congruent to 1 mod 12. So yeah, indeed this formula works in this case. So yeah, that is Euler's totient function. Euler's Totient Theorem. So yeah, we have verified that it works. And now we're just going to try a problem related to this. So, for example, 11 to the power of 98. Find the remainder when 11 to the power of 98 is divided by, let's say, 39. So again, pause this video and have a go at this problem first on your own. So the solution is, so first, we want to use this Totient Theorem thing. So let's look at the totient of the modulo first. So totient of 39. Oh yeah. So 39, we know that 39 is equal to, its prime factorization is 3 times 13. So its distinct prime divisors are 3 and 13. So totient of 39 is equal to 39 times 1 minus 1/3 times 1 minus 1 over 39. And that simplifies to 24. Does it? Wait. Yep, it does. Oops, sorry, that has to be a 13. That has to be a 13. So that will be equal to, that indeed will be equal to 24. So totient of 39 is equal to 24. Then that means, and we know that 11 and 39 are coprimes, so we can set A to 11 and N to 39. So then 11 to the power of totient of 39 is equal to 11 to the power of 24, which is congruent to 1 mod 39. And then we can set both sides to the same power. So again, we're building a power tower here, all the way up to 98. So to the power of 4, because the largest multiple of 24 that is less than or equal to 98 is 96, which is 24 times 4. We set both sides to the power of 4 to get 11 to the 96 is congruent to, that's still a 1 mod 39. And then we just fill the rest by multiplying 11 squared to both sides. So that will become 11 to the 98, and multiplying 11 squared on this side, it becomes 121 mod 39. And so this modulo 39 is, let's see, modulo 39. So 39 times 3 is equal to 117, which means that this, when divided by 39, the residue will be equal to 4. Will be congruent to 4 mod 39. So therefore, when the remainder when 11 to the 98 is divided by 39 is equal to 4 by using the Euler's Totient Theorem. So yeah, that is how you use Euler's Totient Theorem, by building a power tower. Yeah, if you want to have a better understanding of how to apply this method, well, then yeah, take a look at the FLT video, because in that video I talk a lot about this method. But here I will not talk about it that deeply, because yeah, it was already discussed in another video. So yeah, that's one problem. And actually, now I'm going to show you a proof. Now I'm going to show you how the Euler's Totient Theorem relates to FLT, to Paracel Theorem. So FLT, yeah, before you watch this section, yeah, I recommend you to look at the FLT video first, because yeah, it uses FLT here. So FLT states that, Paracel Theorem states that A to the P minus 1 is congruent to 1 mod P if A is not a multiple of P and P is a prime. And it's pretty obvious that A shouldn't be a multiple of P, because if A is a multiple of P, then this whole thing is 0. And yeah, we're not going to talk about that too much. So here, we see that by Euler's Totient Theorem, A and P have, so again, since A is not a multiple of P, A and P have to be coprime, since P is prime. So A and P are coprime. And let's see what the totient of P is. So the totient of P. And the totient of P is equal to P times 1 minus all of its prime divisors. But we notice that since P is a prime, its only prime divisor is itself, because P is a prime. So totient of P is equal to P times 1 minus 1 over P. So that is equal to P minus 1 over P. And that simplifies to P minus 1. So by Euler's Totient Theorem, a to the power of totient of P is congruent to 1 mod P. But we found that the totient of any prime is equal to 1 itself minus 1. So that is equal to saying that a to the P minus 1 is congruent to 1 mod P, if A is not a multiple of P and P is a prime. So yeah, we just proved FLT using Euler's Totient Theorem. And yeah, we can see here that they both relate together. So most number theory lectures and classes and textbooks, they usually talk about Euler's Totient Theorem and Fermat's Little Theorem at the same time, because they relate like this. And they also use the same kind of techniques as well. So yeah, that is a proof of FLT using Euler's Totient Theorem. And there's actually much more interesting proofs of this theorem, but yeah, there's a lot of them that are much more interesting than this basic proof. So yeah, this is Euler's Totient Theorem, and yeah, hope you enjoyed this video, and see you in other number theory videos, or yeah, any other videos in my channel.